Swayam Prabha. Digital India. Educated India.
So I'll start now. So that's the beauty about scientific and mathematical approach. Whether you are studying a million water molecules, or you are studying the predicting about IPL teams, or you are looking at stock market, sometimes the same mathematics goes in all. There is a common binding mathematical structure. You won't appreciate it if you look at it piece by piece. But this common idea of cooperativity, how can one bring it in mathematical equations? Something very interesting. As you go along, you should look into that as a research topic. The last thing I'll mention, water conducts electricity, was discovered by Grothus back in 1806. And this is not due to electrons. The schematic explanation is here. As I said, there is auto dissociation of water, that is, one proton can come out, that one arm can come out. That arm can come and grasp the leg of one water molecule as shown here, and then there will be a series of rearrangements such that the extra arm attached here, the rearrangements happen for thousands and millions of molecules. At the end, one arm fell off from the opposite end. This very rapid way of transporting a proton is called the proton, or a hydronium ion is called the Grothus mechanism. That is responsible for water transport in the current transport in water. Water is not the only system which has hydrogen bond. All of you have studied chemistry, and there are so many systems wherever there is such distinction between electronegativity, like hydrogen and fluorine. You can have HF, a very dangerous but interesting system. FH is the usual bond between them, but then this is the hydrogen bond. It forms a linear structure as depicted here. This is an alcohol, HOR, and like ethanol or something, and that also forms a linear structure. The special thing about water is not the hydrogen bond. Hydrogen bond is there in so many liquids. It's there in alcohol, all alcohols. The special thing about water is its ability to form 3D hydrogen bonded structures, and that's because of the local tetrahedral coordination. It's not possible in other systems. Most commonly people think it's hydrogen bond, so that is special. But if hydrogen bond is so special, it's there everywhere. But life is made up of only two things, carbon and water mainly. Carbon, because of its different hybridization, can form linear structures, sheet-like structures, 3D structures, everything can be made. Similarly, water can also make 3D structures, and life fundamentally is a 3D object, and that's the reason why water and life, water and carbon are fundamental to life. The next thing I'll talk about is this interesting problem solved by Linus Pauling, which led to a good understanding of what is hydrogen bond. This is the missing configurational entropy of ice. I have shown that every oxygen has two hydrogens which are part of the H2O molecule, which are covalently bonded, but there is an ionic character, and every water molecule has two hydrogens which are bonded to the lone pairs. Right? There are 4 hydrogens for every oxygen, 2 belonging to H2O, 2 belonging to the neighbor. For convenience, though we have to draw the molecules with the big bellies and hands and feet and the hexagons and so on, but for convenience we can put them on a square lattice. Some things are still there on the square lattice. We can put all the oxygens at the vertices. Then we can have arrows pointing in, means those hydrogens are closer. Those are the ones belonging to H2O molecule, and 2 of them pointing out. Those are the ones which are participating in the hydrogen bond. They don't belong to that H2O, but to the neighbors H2O. And this kind of rule has to be observed for every oxygen. These rules are known as ICE rules. The ICE rules say every vertex has 4 arrows. Forget about water now. Every vertex, 4 arrows, two arrows inside, 2 arrows outside. What happens for one is determined by the neighbors, and which in turn is determined by the next neighbor. So there is complete cooperativity across the whole thing. You can't change one by changing everything else. Let's look at what happens at one of the vertices, oxygen. Is this allowed? Don't worry about bond angles. I am just talking about numbers. This is allowed? Yes, it is allowed. These 3 together form H2O, and these are the neighbors. This one is not allowed. Why? 3 are coming in, only 1 is going out. Also some other things which are, all are coming in, not allowed. This is allowed. Okay. So like if there are n water molecules, there are n vertices, and then there are some things are allowed, some things are not allowed. N molecules, n vertices. Sorry?
The water molecules at the surface, they won't have neighbors.
Edges, here you mean edges, right? Like these, right? So imagine this is so, n is so large that we don't have to worry about the edges. If n is small, then the edge is important, but this is growing as n square, whereas the boundary is growing only as n. You make n 100, boundary is 100, but area is 100 into 100. The number in the bulk is always increasing. How many allowed configurations? Maths problem. Forget about water, vertices, arrows, and how many do you think are allowed given all these rules? I'll let you spend half a minute on this. If you are attempting, that is good, because it's a very hard problem, and Linus Pauling wrote a paper on this almost 100 years back. Okay, any ideas? Are you there with the number? How many ways you can arrange them? All, if there are n of them. Okay, let me ask, is it 6 raised to power n? Why is it 6 power n? Right, I get it. So 6 to the power n, as you said, very close to the answer, assumes all the vertices are independent. Take one molecule, but remember the IPL team story, you change one, the other thing changes. So it's not 6 to the power n. 6 to the power n assumes all independent. Take any one. First of all, I want to explain to all, because Adi has given this answer, but how we come to 6 to the power n. Look at this, one arrow is in. Let's begin with that. One arrow is in to this left side. Then there are 3 ways to find another arrow in. It should be either here or here or here. Once 2 of them are in, the other 2 are automatically frozen. I don't have to talk about them. 3 ways, and this arrow could have been out. So then again 3 ways. This could have been out, this could have been out, this could have been out. 3 plus 3, 6 ways to construct. And n molecules, 6 ways for each molecule, 6 to the power n, if they were independent. But if they are not independent, then the neighbors decide something. This is not exact. Whatever I am saying is approximate, and it's the following: chance, chance that the adjacent molecule will permit a certain orientation. If I look at any one orientation, will the adjacent molecule permit it? Example, if I am looking at this orientation, is one of the 6 orientations, and here it could be in or up or down depending on the neighbor, and this could also be in or this side depending on the neighbor with half probability. The neighbors are influencing, and there is another factor of 1 by 4. So it's 6 by 4 to the power n. It's an approximate result. For exact result, there are numbers of papers written on it. It's a very hard mathematical problem, especially if n is finite, and then or if n is very large, also people have written out series. If you are those who are among those who are inclined towards mathematical physics, this will really excite you. Start trying to find the exact numbers. And then the number of configuration, how many different ways we can arrange this, 3 by 2 to the power n. Yeah.
Sir, could you explain why the probability is half in the previous of it allowing a configuration?
So we are assuming 6 are allowed, but whether that configuration can be taken depends on the neighbor. If I say this configuration is taken or not, there is a chance it may not be taken due to the effect of the neighbor. Otherwise they are independent. Somehow I have to bring in the idea that the neighbor affects. That is half, and similarly this is also half. So then the half into half, because I am taking both in, so simultaneously both are in. Now this is an approximate thing, it's not exact. And then if you are familiar with entropy, then that is Kb ln omega, and the entropy is found here. Entropy is not directly measured, but in specific heat experiments, people were having this missing number. Whenever they compared, they heated up ice from low temperature, took it to water, and then brought it to gaseous state. They measured the specific heat and got the entropy. Then they took water and directly measured the entropy, the vapor. Those were not matching. So that was the missing quantity, and Linus Pauling was able to show that this is exactly that quantity which was missing. Then I come next to the high dielectric constant of water. There is, I am sure all of you, because you are from 11th and 12th standard, you would have heard about the dipole, separated positive and negative charge, and there is a dipole moment which is given by Q into the separation D. If you take, say, a hydrogen atom, it does not have any dipole moment. There is a nucleus Q plus in the center, there is an electron cloud surrounding it, Q minus. So it appears there is a separation of plus and minus charges, but if you do the averaging for every Q minus at the top, there is a Q minus at the bottom, and from the symmetry, the total dipole moment is 0. If you apply an electric field, the electron cloud can be displaced. The nucleus is harder to displace, the electron cloud gets displaced, and that is called as induced polarization. A dipole moment is induced by applying an electric field, as depicted here. And then there are systems, as I have talked about, water, which have a natural dipole moment. Even if you do not apply an electric field, they possess a dipole moment. That is the permanent dipole moment, as depicted here, with 0 electric field. Skip this. So when there is no electric field and you have, well, the system like water, dipoles are pointing in different directions depending on the orientation of the water molecule. In ice it is still fixed, but in water it can be quite random, and it will enter into voids, and broken portions will be there, and so on. The net dipole moment is 0. Now what happens to a dipole under external field? This is a dipole and a field is applied. We can look at the force on this dipole. The force is 0 because, yeah, there is a torque present. The force is 0 because this charge is being pushed to one direction, the other charge to the other direction, the net force is 0. But the net torque about this point O, well, one can compute R cross F, and that turns out to be something non-zero. So it can rotate. The electric field is trying to align the dipole in that direction, but does it succeed? Will it work? Do you think if you apply the field, all the dipoles will turn to the same direction? They will always. And how tiny a field you should apply that all will turn to the same direction? Okay, so this is related to the concept of chemical potential. For instance, I will just mention a slightly different problem. You have gas molecules in a container and you have gravitational field. Now it is clear that the ones at the top have more potential energy, the ones at the bottom have less potential energy. But they don't just fall like marbles. They could have to lower their potential energy. Everything falls under gravity. But that doesn't happen. This is something not happening with gas. There are two forces. The gravity pulls it down, but their tendency to diffuse takes it up. And that's the randomizing effect of temperature. In statistical physics, we talk of a gravitochemical potential, which is same across everywhere. The same kind of analogy can be used with the electric field acting on these dipoles at a finite temperature. The temperature is trying to misalign the dipoles, it's trying to randomize it, just like it is sending the gas molecules up. And electric field is trying to align it. And in a very important idea in thermodynamics is the Boltzmann factor, which gives us the probability that one or the other state will be occupied. The probability that the energy is equal to U is given by e raised to power minus U by kT, not just for this problem, for every other problem you will come across. That means if the energy is more, the probability of going to that state is less, but it's not zero. Therefore, gas molecules can be there high up where they have some potential energy compared to the gas molecules on near the floor. There is a change in the probability, that's all. Large U is less favored, so you go away from the Earth's surface, the atmosphere becomes rarefied, and large temperature enables more population. If you heat up, then more gas will go to the top. All of this can be seen built into this equation. So this is a cartoon representation of the idea. The electric field is trying to really align them in all one direction. The dipoles are responding in their own way. They are trying to oppose this. They are creating their own polarization, and that is opposing this field. As a result, the field, if you consider a point charge and there is an electric field due to the point charge, that decays much faster due to polarization in the medium. That is, you bring in this dielectric constant or relative permittivity, epsilon. Now the field which in vacuum was going as 1 by 4 pi epsilon naught r square will now go as 1 by 4 pi epsilon naught into epsilon. Epsilon is greater than 1. Relative permittivity. And the explanation of relative permittivity is something like this. So if you have, say, water molecules, for instance, so they have like minus and plus, they have dipoles. If you have a negative charge inside water, then that is going to cause these water molecules to arrange around it in a manner that the field of this negative charge is decaying very rapidly. This is the process of screening, and mathematically it's the 1 by epsilon which comes. Water has a very large dielectric constant, 80 is the value under normal conditions. Of course, it is very difficult to estimate just by the simple considerations, because this also the field created by the dipoles of the water molecule. When they arrange, they create a field. First you apply a field, then they arrange, that changes the field which is effectively applied to any water molecule, then again that changes. So it's like an infinite feedback loop. So very hard to find out exactly what happens, but the number is close to 80 experimentally. This is also something you utilize in your day-to-day lives. For instance, you operate a microwave. It is related to how the dipoles are responding to a rapidly changing field. The microwave involves frequencies in gigahertz. The electric field, the magnetic field are changing at very large frequency, and then the dipoles may not be able to respond very well at those frequencies. When they are not so easy to respond, then there will be friction between adjacent dipoles, which will cause kind of a heating effect or absorption of power. I'll skip some of the slides. I'll skip this in view of time. Yeah. Okay. Yeah, I'll come to this. So this dielectric property, where some of the context where still research is going on in the context of the high dielectric constant of water. One of them is the following. The dielectric constant is 80 only under the ambient conditions, but if you change pressure and temperature, in this diagram you can see it's scarcely 80, only here. If you change the density, change the temperature, it can be very, very different. It can come down to as low as 10 here, it could be very small, less than 10 at under different conditions. So in this study, they looked at what are the conditions deep inside the earth, the pressure and temperature in the upper mantle, and they found that certain metals, metal carbonates, MCO3, which are insoluble in water under ambient conditions, can become soluble in water under those conditions, that can transport carbon from the upper mantle to the lithosphere. So through the water cycle, a carbon cycle is created from deep inside the earth, which is again then related to fundamental questions like how life originated on earth, where the source of carbon came. So there are such deep problems related to the dielectric constant of water. And the fact why salt dissolves in water is also related to the high dielectric constant. So just we'll have a quick look at why salt dissolves in water, but you are welcome to give a short answer. It breaks the bonds. Any answers why salt dissolves in water? Right. But does it always happen, or it has something to do with some property of salt or some property of ionization energy? Right. Okay. So let's look at this NaCl, Na plus and Cl minus. First of all, forget about water. Let's look at NaCl. There is ionization of Na plus, extra electron going to chlorine, so there is electron affinity. If you look at their energies involved, there is energy required to pull an electron outside sodium, energy required to push an electron inside chlorine. Take the net sum, it's actually positive, which suggests that NaCl shouldn't exist. Am I missing something? Forget the lattice, just take NaCl, one Na, one Cl. Forget water, just NaCl in vacuum. I'll come to the larger lattice, but this should also exist, NaCl. Absolutely. Yeah, so they are not isolated, so absolutely. So there is also this electrostatic interaction energy between Na plus and Cl minus. It's not just ionize one, put the electron to the other, but you also created plus and minus, and they will have interaction, electrostatic interaction. So NaCl should exist, thermodynamically allowed, and it actually exists as a, you can extend the idea to an ionic crystal. It exists as a crystal, but I just showed a simple calculation that exists. Now if you look at Na plus and Cl minus, actually we will do the calculation for a crystal, but now we will just do it for one Na plus one Cl minus. Then the potential energy of interaction is this, is less than 0. If you bring them closer, it becomes even more negative. So they should just collapse, but that doesn't happen. Why shouldn't they just collapse? You have plus and minus. So just okay. So even before the nuclei repel each other, quantum mechanics takes electrons start repelling each other. So ions should collapse, but they don't collapse. Salt exists, we all know. And there is a repulsive term. That repulsive term is very hard to explain in terms of why it is r to the power n. What is n? But I could say it is of quantum mechanical origin, not to be discussed in today's class, and it's empirical. Empirical means people have done experiments and found out the value of n. If we plot this expression, it's 1 by r and 1 by r to the power n, then the attraction is the negative potential energy, 1 by r. The repulsion, quantum mechanical, empirical, r to the power n is positive. and the net sum is here, right? You can combine the two, and this is the equilibrium distance between Na plus and Cl minus, because that's the minima of the energy. That is where it should exist. This is the distance between Na plus and Cl minus. Water now has this high dielectric constant of 80, and that should suppress the electrostatic interaction. It doesn't affect the quantum mechanical term, that remains what it was. But if the water molecule could be present between Na plus and Cl minus, it's very, very tiny, let's say it could enter that, and if it still we allow epsilon to be 80, now we can question, will it still be 80 when it is just sitting in between? Then this curve should shift up. The 1 by epsilon term will appear in the electrostatic interaction, and then the minima of the potential energy will shift away. Minima was here originally, now it has shifted little to the right, and more importantly, this minima of the energy, the value of the minima, which was very deep and large earlier, so many electron volts, now becomes less than 3 by 2 kT. So the thermal energy is sufficient to separate out Na plus and Cl minus. Eventually, it's a consequence of the high dielectric constant of water that it is able to push apart Na plus and Cl minus together with the thermal energy of the ions. And that's why salt dissolves in water. And once it has dissolved, it gets solvated as pictorially depicted here. Na plus carries a shell of water molecules around it, first hydration shell, a loosely bound second hydration shell, similarly for chloride. Okay, skip this. Yeah, as you mentioned, there is actually a crystal. We should do all the calculation for the crystal. I will just mention, for lack of time, that this is a very interesting mathematical puzzle. Try computing this series, by taking as one Na plus has 6 neighbors in this crystal which are chloride, and then there are so many neighbors which are next nearest neighbors which are sodium, and so on. And then just write down a simple series which will look like this: 6 neighbors at a distance r, 12 neighbors of the same sign at distance under root 2r, 8 neighbors of this different sign at under root 3r, and so on. And you will get something which oscillates very rapidly, doesn't converge. So the solubility of ions is understood, why sodium chloride crystal can dissolve. I'll skip some parts here. Yeah. So yes, maybe I can discuss this. So if you look at how much of sodium should dissolve, again you have a kind of a Boltzmann factor. The same Boltzmann factor which I used to describe the gas problem and the arrangement of dipoles also appears here. This is your electrostatic interaction term. Actually, it's a free energy term, but the electrostatic is the most important one. You have water molecules coming in between NaCl, Na plus and Cl minus, separating them off, and then this is the free energy change, E square upon 4 pi epsilon naught r. Then I should also put the epsilon of water. The final energy state and the initial energy state, the difference between them is the change in the free energy. If I look at this, then the solubility in mole per mole is given by this factor. That is, if the free energy change is much larger, the more it will be soluble, if it can induce a big free energy change. And if you plug in the numbers, with this very simple calculation, you get very close to the actual value. How much of salt dissolves in a liter of water is 360 grams. And that number comes, if you do a calculation, you will come to something like 280 or 240 grams, just with this very simple expression. Here is a plot of the solubility of NaCl with epsilon, all on log scale. Water sits out here, and the same curve explains its solubility in all different systems, in alcohols, in this is methyl formamide, and so on. The dielectric constant plays a central role in how much solubility any salt has in water. And the same idea is extended to the ability of roots to penetrate the soil. The soil is composed of clay and organic matter, and they can also possess charge. So we say they can be like charged colloidal particles. When water enters, it diminishes the interactions between these colloidal particles, just like it separates Na plus and Cl minus, screens the interaction between Na plus and Cl minus, it screens the interaction between clays and organic matter. So they become like loose, and because a tiny amount of water can make the soil loose, the roots can penetrate the soil. So another reason why the dielectric constant of water is so important. The fact that trees can send their roots to the soil is related to that. There's also another thing, I mean, I just talked of dielectric constant, but there is entropy playing an important role. Entropy is related to arrangements, and whenever you bring in any ion that creates a hydration shell, causes the hydrogen bonding to change around that particle. It makes it more ordered locally. More ordered is not favored, it should be more disordered, which will be favored. So this part helps to determine, for instance, structures like clathrate cages, where you have water molecules forming a cage with a different hydrogen bonded network than for bulk water around, say, a molecule of say methane gas. So may I also know what is shown in the picture, because some of you are into chemistry, I hope. Spot the difference. I think this is it's a small difference, right? At least you will agree. I have not shown what are these circles, filled circles. They are different functional groups. Different groups are there. I have not told you what those groups are, but there is not much difference. This is the difference, right? Somewhere here. Okay. So these are sugars, and they have some names. Fine, no problem. D-galactose and D-talose. Just this tiny amount of difference in their arrangement makes one hydrophilic and other hydrophobic. That is, the hydrogen bonding network of water is so sensitive. It forms a hydrogen bonding network all around it. In one case, the arrangement is a little different and it likes to repel. It doesn't like the arrangement. The other case, it is favorable. It forms easily soluble sugar. Then there is also the lotus leaf effect. As you have seen, the bubbles forming, again related to how the water molecules are interacting with the surface, how much of it is energetically favorable or not energetically favorable. So now I will spend just another 10 minutes on some research that we do here before concluding. Confining water means trying to put water in kind of a cavity or place where the space is very restricted. Up till now, whatever I discussed was about bulk water, the water in your water bottle. So for instance, I could take a strand of hair which is 100 micrometer, that's the dimension. If you don't have a feel for it, you can think a strand of hair has been put, and you take some solid object in the bottom, another solid object at the top, and then bring it close together. It forms a small space, right? You will agree that space is very small, very hard to create this kind of space. But if you think in terms of how many water molecules are there, the van der Waals radius of a water molecule is 2.7 angstrom, which means there are more than 1 million water molecules in the vertical direction alone. With this geometry, you are not really confining it. It's still like bulk water. What I need to make it is 1 million times thinner, and 1 million times thinner than human hair is very hard to make. That is where some naturally existing systems are helpful, and these are two-dimensional materials like graphite or like graphite, where the separation is less than a nanometer. And if we could put water inside these spaces, then it would be very different from the bulk water. So this is some work we have done here, and the people who have done the work also are at the back. I will just tell about the work. Okay. Yeah, Vikas and Anjan are here, right? So here I was pointing out, this is the separation between these graphite-like sheets is about 6 to 10 angstroms, or 0.6 to 1 nanometer. I have taken a cross section. The sheets are there, say coming out of the plane of this screen, and in between them you could just have a few water molecules. Some are hydrogen bonded to themselves, some are free floating, and so on. Other people have studied, for instance, water inside a carbon nanotube, where you can have a single wall carbon nanotube, you can have a line of water molecules which are hydrogen bonded. This bonding is so different than the hexagonal arrangement I had shown you much earlier. So there was a study 2018, that is few years back, and they showed this very remarkable result. Now to recap, the dielectric constant of water is one of the most important quantities. It is related to its ability to dissolve so many things, right? And I've shown you many other problems. Microwaves are related to the dielectric property of water, how a microwave oven works, right? And also another property is the carbon cycle, a new discovery related to that how carbon can be transported by making something soluble in water which otherwise is not soluble. So many places it is so important. And the dielectric constant is 80. But what these researchers found, they took hydrophobic graphite-like sheets, the top and the bottom, which was, they kept on diminishing the distance. And then they found the dielectric constant reduced to as low as 1.8 from 80. That means that water is not the water in the bottle, it's completely different water. Why does this decrease to 1.8 and not 1? Could you guess? Why doesn't it go to the value of 1, which is there for air or vacuum? It's because there's still an electron cloud that can be displaced. I said, no, there can be induced polarization. The dipoles can be induced by pulling the electron cloud. As long as water is there, the electron cloud can be displaced. But now the dipoles don't rotate. Imagine a water molecule sitting here. The electric field which is applied between these two capacitor plates, which are so tiny, the distance between them is a nanometer. When the electric field tries to orient them in that direction, the walls are repelling that, and they won't allow this dipole to be oriented. You can still orient them in the plane, but you can't orient them out of the plane. That brings the dielectric constant from 80 to 1.8. So we looked at a very related problem, because this study was on repelling walls which don't like water. But we looked at walls of the same size, but those which liked water, because they were decorated with oxygen rich groups. And Vikas, who is here, you can see his picture, yeah. Also you can see him here. So he did this study. The number of tools we used, dynamic vapor sorption is a technique where you can study how tiny amounts of water get loaded and unloaded in a system under controlled humidity and temperature conditions. And we looked at how the spacing is exactly controlled at the sub-nanometer level. We had, I don't have the picture I wanted to show, so we had a miniature capacitor. By applying the electric field, we could see the orientation of these dipoles, whether they orient or not. And the important thing we found is, in this case, the dielectric constant is not as low as 1.8, but it is intermediate to the bulk value and some value which is still fairly large. So then I'll also mention very briefly other students who are sitting at the back, research scholars. They are looking at other systems. I mentioned about the Grothus mechanism, a rapid way of transporting protons. So Anjan Das, who is sitting at back there, looks at the Grothus mechanism in hexagonal boron nitride of how protons can be transported so rapidly just by adding a tiny amount of water, 5% by weight, and the resistance will change by 10 to the 14 orders in magnitude. And Devender, he works on interaction of water with molybdenum disulfide. There are many tools we use, so just I'll flash the names. Some of them are so simple that I could just have it here and I can show you. For instance, this is one of the membranes made in our lab, graphene oxide membrane, through which we study the water transport. And there are simple systems such as this cell on which you could mount the membrane, and there is a column of air. You could apply pressure up to 70 bar. You could cause the liquid to flow through the membrane. So the water molecules are moving through sub-nanometer spaces, and we could measure at what rate they are flowing out and whether they are filtering out the ions. It's called a pressure cell. But then there are other tools needed. We use a lot of impedance spectroscopy and dielectric spectroscopy, Raman spectroscopy, and so on. Then there are tools like neutron diffraction, not so easy to hold it in the hand and show. I need to have a nuclear power plant along with it, which is there in a few places. Future prospects, many important things are still not understood. So I have talked about the orientation of the dipoles leading to the dielectric constant, how that those two things are connected. Take different polar liquids like octanol or nitrobenzene. When you freeze the liquid, now it forms a solid structure which is frozen. The dipoles cannot rotate in response to the electric field, and therefore the dielectric constant just drops down. The dielectric constant is related to the ability of the dipole to rotate. That's what happens for nitrobenzene, for octanol, for dodecanol, and so on. For water, another anomalous property, it goes up as if the ice dipoles are more free, and which has led to the question whether the dielectric constant was even related to the rotation of dipoles or not. So what we take for granted is all questionable. Then the context where all this research is going to be very, very important is shown in this picture. It's the cartoon. This is the inside of a bacterial cell, and there are things like all important things people know. This is important for cell biochemistry, nucleic acid, proteins, and then these tiny objects like sugar, ions, amino acids, everything is shown here. Whatever is not marked or not shown in this dark color is water. Water is present as like a constant background, but it is the most important thing because it controls the electrostatic interactions between all of these things. And if you confine it, the dielectric constant is no longer 80, the interactions are very much different. Certain reaction may happen, may not happen, depending on the value being 80 or 1.8 or 20. And in particular, I'll mention that this important problem, a peptide chain can form a very complicated three-dimensional folded structure called protein folding. If this protein folding only happens in the presence of water, and it has to fold in a particular way which is dependent on the exact hydrogen bonding glue, the hydrogen bonding between water and the proteins groups and within themselves. If it folds properly, it forms a biofunctional enzyme. It can do things. If it doesn't fold properly, it's just another polymer. The understanding of this protein folding and the control requires an understanding of what the water does when it is in a confined space. What is its dielectric property, how much hydrogen bonding it has, how many neighbors it has, all these questions are important. What is the density? Is it even a liquid or can it be a solid at room temperature? Are we full of tiny fragments of ice? Maybe. These are the open questions for which people don't have answers, and they are at the frontier of research today. What cell water is like is going to determine the cell's molecular mechanism. And it's really interesting to think about that these kind of tiny spaces exist everywhere in our human body, and we know so little about it. Imagine that ice is flowing in your body, you may not be aware. The last thing I'll touch upon, though it's very important, I didn't have time to, is you just Google most polluted rivers of the world. Unfortunately, that's what we have done to water. Water is highly soluble, likes to hold different things, and the Ganges and Yamuna are among the ones which top. And this is a very important problem, in practical problem. I didn't touch upon any of these things. How to purify this water. Since we are here at IIT Madras, I should also mention that a very important effort has been done by the government around this place, which is the Adyar Restoration Project. There is an Adyar Punga, nice place nearby. You should visit that and see how they have restored a highly polluted river and made it quite a beautiful place with lot of pelicans can be seen in that place. This is some thing that all of you should think about contributing and making the earth a much better place. So thank you for your attention. It's also a water break, and if any questions are there over the next couple of minutes, I'm happy to answer. Anything you would like to ask from the beginning to the end? We had a journey covering many things. Yes, yeah. How the thermal energy helps in solvating. So there is this interaction energy between Na plus and Cl minus. You can take the whole crystal, you can do the calculation. There is a non-converging series I mentioned. You make it converge, you get a number. That is the energy. Now water molecules can enter between the spaces because they are so small. That reduces the interaction energy. If it can be brought so less that it's lesser than the thermal energy, which is by a theorem called equipartition theorem, they are given us, each ion is given a 3/2 kT energy. If it is less than that, then by thermal agitation it can overcome that bonding and it can become the interaction energy of the plus and minus. Yes.
Sir, at the scale of like a couple of water molecules, like one water molecule or 3-4 water molecules, will there be any quantum mechanical effects which are observable, which might change the behavior from classical?
So up till now, all the description I have given is all classical. Whether we need quantum mechanics to explain some aspect of this, I don't think quantum mechanics is really required for the description that we have given. For the kind of phenomena that we have explored, maybe if you are looking at water under very high pressure, looking at the quantum mechanical repulsion which is responsible, eventually that part of the curve decides where the equilibrium separation is. So whenever you have chemical bonding and all, quantum mechanics is there, but when you look at their arrangements, and this are determined by maybe more of classical and thermodynamics and statistical physics.
You told us about the mysterious configurational entropy of ice.
Right.
It is because of its H bonding, right?
Yeah, it is because of the tetrahedral coordination and the H bonding.
So there might be other compounds which follow the same method. So
No,
will they also have this
no,
mysterious
I emphasize that there are no other compounds. Mostly there are no other compounds because these three-dimensional structures are not formed by other systems. I showed you HF, I showed you alcohols, they all form linear structures.
It's only FO and form the
HF forms a linear chain. So the same thing will not apply to that. Maybe one last question if you have. Okay, if not, then thank you. It was pleasure talking to all of you.